So at the very beginning of the section, we did say that not only did we need a couple of different rods and a piece of silk and a piece of wool, we also had a piece of wood and then we had a piece of metal. And now we're going to look at insulators and conductors and kind of how they work. So we're going to charge a plastic rod with wool. And when we do that, it acquires kind of an excess negative charge. If I touch that rod to a piece of metal, I notice that when I take that metal and I hold it close to um, a, uh, a plastic rod that's been charged, that they will repel each other. So these two things will push apart on each other. And that just shows you that it really truly did acquire a charge that is the same as that plastic rod. That's experiment number 6. Experiment number 7, now what I'm going to do is the same thing. I'm going to take some negative charge and I'm going to have some excess negative charge on the plastic. That will move when I touch it to the metal, but then when I touch this to a plastic rod that is in between another metal ball, and then I take this metal ball and I get it close to a rod, I notice that there's nothing that happens at all. Okay, so this is a negatively charged plastic rod. Get it close to this metal ball, but I don't see anything happen. So the thing that we can take out of this is that this rod didn't allow any charge to go from the first metal ball to the second metal ball. So that'll be important here later. In experiment number 8, I'm going to do the same thing. Take the plastic rod, I get a little bit of charge on it, touch it to this metal ball, which then makes this one a net negative charge. There's a metal rod then that allows that charge to transfer, and then it's transferred over to the other metal ball. And then when I get a plastic rod over here that's hanging by a thread, and I notice that these two things do repel each other, that shows that this thing allowed charge to transfer through. So those are the experiments kind of that they want you to think about in order to talk about insulators and conductors. So here I am transferring charge from one object to another by using touch. Okay. If I want to discharge something, discharging is removing charge from an object. So for example, in that very first thing when we had John Travoltage, so here's John himself, when he touches that door handle, we are discharging. So we're allowing those negative charges to move from him onto that metal door handle. Conductors are things that we can see that have charge move them through them or along them very easily. Insulators do not. Okay, so this is where charge is very immobile. Okay, it doesn't really work very well. Glass and plastic are insulators. Metal is a very good conductor. So for example, if I have a metal wire, okay, and typically we don't want to touch that metal wire, so what we do is we put a piece of plastic or rubber on the outside, and therefore the charge can go through, but it doesn't affect the person holding that wire. If you hold onto the bare wire, you might get a little bit of a shock. Something else that is an insulator is glass. And so on a telephone pole, typically what you'll see, telephone pole will go up, whoops, telephone pole goes up, it's a twisted pole I guess, and then you'll have a piece of wood here, and then there's a little piece of glass on the very top, right here, and that's where the wire, the bare wire, can actually attach to it, and then it goes on to the next telephone pole. That glass is an insulator, and so it doesn't conduct any charge. If it was metal, it might allow some of that charge to travel down to the wood, and if the wood is wet, it would electrocute anybody standing down on the bottom, which would not be a good thing at all. So those are insulators and conductors. So we know there's a couple different types of materials. Conductors are materials through or along which we can have charge easily move. Insulators are materials in which charges basically just stay fixed in place and they are not allowed to move. We can also transfer charge from one object to another by making them contact or making them touch each other, which is really important. For the next part, this is electrostatic equilibrium. This is where we have charges. They're on an isolated conductor. They are in static equilibrium with the charges at rest. A conductor in this type of equilibrium will kind of stay there. There might be a little bit of movement in in that object in order to achieve this equilibrium, but it happens so fast that we really don't see much. So for example, if I take a balloon, so here's my balloon, and I rub it on a piece of carpet, so here's my piece of carpet, the charges will move from one place to the other, but then this thing will become in electrostatic equilibrium. But we'll have some charges on one side that might be negative and positive charges on the other side. But after some time, these move very quickly and they distribute so that that interval is very, very brief. And now we can say that that balloon is in equilibrium or electrostatic equilibrium. The next thing that we'll see here is a quick check. It says we have a couple of different objects, A and B. Object has a net charge while B is uncharged. Based on this information, they want to know what is each of the two things. And so if we look through this, we're going to notice that there's not enough information for us to be able to tell. And it's mainly because there is no movement, okay, movement of charge. So there's no movement of charge in this example. It just says that A has a net charge and B is uncharged, but it doesn't tell us anything about movement. So we really don't know if these things are insulators or conductors. So we really can't say anything about A, B, C, or D. We can just say there's just not enough information for us really to know what's going on. Polarization. This is called charge polarization, and what we're doing is we're charging something like that rod. So here we've got a positive rod, and we have a sphere that has both positive and negative charges in it. So we say that it is it's neutral. So it has an equal amount of positive and negative charge, but when I get this rod close to it, it actually attracts the negative charges, and then the positive charges kind of remain where they are. So we get a net movement of negative charge to the side. So the rod, it's really important here, it does not touch the sphere. And because it doesn't touch the sphere, we are allowed to just move these charges from one side to the other. The negative charges are at the top of the sphere, more strongly attracted than the distance to the rod, than the distance positive charges. And so now we have a net attractive force. So that net attractive force is up towards the top. And so it's pulling that metal ball up just a little bit. The polarization force arises because the charges in a neutral object are slightly separated, and it's not because the objects are oppositely charged. Okay, so we're separating charge here. The polarization force between that charged object and a neutral one is always attractive. Okay, so it will never be repulsive. So you always have those two things come towards each other. All right, so let's go on a little bit. Take a look here. It says metal spheres 1 and 2 are touching. They're both initially neutral. We have this charged rod. It's brought near the two. It's then removed, and then the two spheres are separated. They want to know what are the charges on the two. Well, when the rod gets close to it, we do have a net negative charge on one side of the system and a net positive charge on the other. But the instant we get rid of this, the charges move right back where they're supposed to be. And so in the end, our answer here is both of these spheres will have a 0 or a 0 net charge. So they both have negative and positive charges on them, but they are equal on each one. Now, if we change this scenario a little bit, if we take this charged rod, we get it very, very close to the two, and then we separate the spheres. Now we have something different happen. So let's say that we have negative charges, more negative charges on this side, which leaves more positive charge on this side, and I separate the two. So this is one thing they don't show you. They've separated them with that rod still there. So we still have the rod right here. So this is positive. Then this one, the negative charges actually stay on this rod and on the first ball, and then on the second ball, because they're not there, we have a net positive charge. So afterwards, the charges on the sphere are a little bit different. So we'll notice that the answer here is Q1 is going to have more negative charge, and Q2 is going to be more positive. And that's essentially what we did when we separated them. We left some excess negative charge here, which means we have excess positive charge on sphere number 2. And that is 20.5. This is a really great picture This is a picture of the same type of thing that's happening. I get something positive next to two metal spheres. I have a net movement of electrons from B to A. And then if I separate the two, you'll notice that I have a negative A sphere and a positive B sphere. And that's essentially what happens, which is really kind of cool. You can do the same thing with a negative object. So you get a negative object close to the system. We pull those positive charges to one side. The negative charges, actually we're pushing the negative charges away. We're really not pulling these positive charges toward per se. But they are slightly attracted to that negative object there. When we separate the two, then we end up with just the opposite that happens. And that's charging by induction. So let's look at 20.6. I have identical metal spheres here, initially charged as shown. P and Q are touched together. So when I touch these two together, I'm going to have essentially 4 plus negative 2, and that's going to give me a positive, so 4 plus negative 2 is going to give me positive 2 nanocoulombs. And then when I get close to, essentially then I have spheres Q and R touched together and then separated. So now these two are together. This positive 2 net charge means that I end up on P with a positive 1, and on Q I have a positive 1. So 4 minus 2 would give me that net charge on P and Q when they touch of plus 2. So I've got equal on each side, so plus 1 here, and then because I now have plus 1 on this one, it's no longer negative 2, and a negative 1 here, when the Q and the R touch, I end up with a net charge of 0 nanocoulombs. And so that's kind of what you will see happen in that little process. And that is the end of that section. Our next section will be on charges, atoms, and molecules.